All right, so today we're going to look at rational functions, topics 1.7 to 1.10. So the big idea on these topics is that we have to factor the top and the bottom, and then we just see what cancels, and depending on that, we graph our asymptotes, our zeros, and our key points. Okay, so let's start now. So whenever you get a rational function, always try to factor first because when you factor, that's when you start to see things cancels out, which results in holes and vertical asymptotes and etc. So that's why the first thing to do is always factor. So now let's look at the first examples. Okay, so end behavior is what we're going to be trying to do first. So if we're looking at this function, 4x squared minus 5, 2x squared plus 7. So the degree of the top, the degree of a function is going to be the greatest degree it has. So for example, in this function, if we have x squared plus x cubed plus 4, then our degree is going to be 3 because 3 is the greatest degree. And if we made that 3x to the 3 plus 4, then our leading coefficient is also going to be 3 because our leading coefficient is the coefficient that comes with the greatest degree term. So if we look, and also let me make this a little thinner if I can. Okay. Yeah, that's better. Okay. So if we look at this function right here, the greatest degree is x squared on the top and x squared on the bottom. So our leading coefficients are going to be 4 and 2. Now, since the top degree is 2 and the bottom degree is 2, the degrees are equal. So let's have the top degree equal n and the bottom degree equal m. So in this case, top degree equals 2, bottom degree also equals 2. So they're equal the same. Here, if you look at this chart right here, it tells you what type of graph we're going to have depending on the values of n and m. If n, which is the top degree, is less than m, which is the bottom degree, then your horizontal asymptote is always going to be at y equals 0. So an example of that would be 3x plus 1 over x squared minus 1. This would be a situation where your horizontal asymptote, which your horizontal asymptotes are basically points where a graph approaches, but it never actually touches. So on this graph, the horizontal asymptote would be at 0. And there would be vertical asymptotes like there, but we'll get more onto that later. But the horizontal asymptote is going to be here, this dotted line, exactly where y equals 0. So the graph would be something like this, where if you look, the horizontal asymptote, one thing about it is it usually is where it doesn't approach, but sometimes in examples like this one, it does have a 0, which is right here. You can see which it passes through the horizontal asymptote. But that doesn't happen on all graphs. Horizontal asymptote is something you can pass by, but you'll never see a graph where the graph passes through the vertical asymptote. So now let's look at n equals m. So the horizontal asymptote is going to be the ratio of the leading coefficients. So here, the leading coefficient of the top function is 4. So 4. And the leading coefficient of the bottom function is going to be 2. So 2. Now 4 divided by 2. Ratio of the leading coefficient. This just equals 2, which means our horizontal asymptote is going to be at y equals 2. So here, let me erase this other stuff. All right, so yeah, we can see that y equals 2. So that means our horizontal asymptote is going to be at y equals 2. So there's our line. So you can see that. Then our vertical asymptotes are going to be somewhere. We won't look too much on that right now. But basically, our graph, it as it's like approaching, let's just say this is our graph. It's not going to be our exact graph, but it's going to be something like that. You can see these arrows indicate that the arrows are going as x infinitely approaches infinity. These arrows are getting infinitely closer toward y equals 2, but they're never going to actually reach y equals 2, which is the horizontal asymptote. Now, if n is greater than m, so if the top is greater than bottom, then it's a slant asymptote. So an example of that would be an asymptote kind of like that. So I'm not going to give you guys an actual function, but here's an example of a graph with a slant asymptote. So we look at these lines, and then this is going to be 1/2, and this is going to be the other half. So the slant asymptote is like any other asymptote where it doesn't touch it, except with the slant asymptote, it's not going to be a horizontal one. And then when n is greater than m by 2, so for example, x to the fourth over x squared, then the asymptotes start getting weird. Like this would be a quadratic asymptote, if you guys can envision that. So it's going to be something like that. And it just keeps going. But that stuff won't be tested in pre-cal, so I'm not going to focus on that too much. So yeah, now we'll move on to some example questions on this topic. And I'll go over these with you guys. Okay. So here's the first example. This is a slant asymptote. X squared plus 1 over x minus 1. So first thing we look at, can I factor this? No, it doesn't seem like I can factor this. So now we look at the things that we can get out of this. So first, it's going to be x minus 1 is going to be our vertical asymptote. So for your vertical asymptote, it's going to be whatever makes the denominator 0. So if you just think about it, right, you know that 0, anything divided by 0 is undefined. So therefore, when the asymptotes are where we can't go, right? So therefore, those asymptotes must be these undefined points. So here, if we solve for x minus 1 equals 0, then we add 1 on both sides. So x equals 1 is going to be our vertical asymptote for this. And as you can see, that's what it seems to be. And then here's our slant asymptote. Slant asymptote gets a little different. So here we have to do long division. So it might seem a little complicated at first, but I'll teach you guys how to do that right now. So we have to divide the bottom term by the top term. And by the way, the first way we know we need to do this division is because the top degree of 2 is greater than the bottom degree, which is just 1. So therefore, it's a slant asymptote. So let's do division x minus 1. So how do we approach this? First, we have to see how can we cancel this x squared? And to do that, we have to subtract by x squared, right? So then we have to think, what does x times what equals x squared? So we can subtract it, right? Well, x times x equals x squared. So we put x on the top, then x squared, and then we have to multiply the whole thing by x. So this becomes x squared minus x. And then we subtract the whole thing. X squared minus x is just, they cancel out. And then uh, nothing minus negative x is just plus x. So x, and then nothing's happening to the 1. So it's just 1. X plus 1. Now we have to cancel this x out. So how do we cancel x out? We just multiply this by 1. So then we add a 1 here. So 1 times x minus 1 equals x minus 1. So then this will cancel out as you subtract, and 1 minus negative 1 is 2. Now 2, you might be wondering, what do we do with this 2? The 2 is just our remainder, and we don't have to do anything with that when a slant asymptote. Our slant asymptote is just going to be this right here, which is x plus 1. So now that we know that's our slant asymptote, we just have to graph it. So let's say this is y, the point where y is 1, that's going to be our y-intercept, and then we draw the line of our slant asymptote. And then to graph it itself, here's how we do it. We have to plug in points for x, different points, and that way we see where they fall, and then it stays within those asymptotes. So what I mean by that, let's erase the rest of it. Now you guys know how to get the slant asymptote and all that, but now it's how do you actually graph it? So So now to actually graph this, let's plug in the point of x equals 0. This will tell us whether if it's x is here, here, or wherever our graph is going to be, right? So x equals 0. Well, 0 squared is just 0. So 0 plus 1 over, and then x equals 0, so 0 minus 1. So this is just 1 divided by -1, which is -1. So that means that whenever x is 0, y is -1. So we can plug that point in. X is 0, y is -1. Now, if you just think about it, right? We know that our lines of this graph are going to follow the asymptotes. And we can't go through the asymptotes, and these asymptotes go on to infinity, right? Arrow, arrow, they go on to infinity. So we can't pass through it. So that way we know that we have to follow this line, right? Like this and this line like this. Because, like, just think about it, right? If one of my points is here, then I can't have my graph go like that. Then it goes through the asymptote. Can't have it go like that, goes through the asymptote. So that way it goes like that. And then for your set the other part of the graph, you're just gonna know that it's the opposite of this one. So if you look at this side, the opposite of that side is this one. But again, we can plug in a point if we want to. Since we know our vertical asymptotes at x equals 1, let's plug in a point at x equals 2. X equals 2, so 2 squared is 4. 2 squared plus 1 is 5. So 5 on the top, and then x equals 2 on the bottom. So 2 minus 1 equals 1. So that way we know when x equals 1, y equals 5. So our point, no, sorry, x equals 2, not 1. X equals 2, y equals 5. So like this point, it's going to be 5. 2, 2, comma, sorry, it's not a grade 5. 5. Okay, and if we just look at our graph, right, our slant graph, when x equals 2 on our slant asymptote, y is going to be 3 because 2 plus 1, 3. So we know that this is going to be greater than our slant asymptote, so we just have our point right there. And when you're being tested on these graphs in pre-cal, they're going to ask you to put like a couple key points. So that's probably going to be your y-intercept and then your x-intercept if you have one. In this case, you don't have one. And then just a couple key points like that. Okay, now we'll move on to the next. Okay, wait. Don't do that. Okay, you know what? We're just gonna over here. Now when it's equal degrees, we see that x squared. So the degree on the top is 2, degree on the bottom is also 2, so these are equal degrees. And to find our horizontal asymptote when it's equal degrees, it's just gonna be the top leading coefficient over the bottom leading coefficient, 1 and 2. So that equals 2. So our horizontal asymptote is going to be at 2. And if we look at the bottom, x squared plus 1, we have to look at where this equals 0 to find out our vertical asymptotes. But if you look at it, let's try to solve for this. X squared equals -1. We subtracted 1 on both sides. Well, now's the interesting thing. You can't square, no number squared is going to be negative. So the solution to this would be imaginary. So therefore, there's no vertical asymptote. So then we just plug in points and then get this graph where it approaches in the horizontal asymptote from both sides. Okay, now I'm going to give you guys some questions. So oh yeah, and before I give you those, let me help you a little on end behavior. So if you look at this graph, right, you can draw out the graph and understand how the graph works. Now we have to look at the end behavior of the graph. Now we went over limit statements in the last class, so let's go over those real quick. So limit, if you look at this graph, as x is going to negative infinity, y is going to approach the horizontal asymptote, which is y equals 2. So y, or you can put f of x equals 2. And then as x approaches infinity, y also equals 2. So that's going to be how you write your limit statements. And yeah, I hope you guys understand that. And here, it's a slant asymptote. It's a little bit different, but pretty much the same. If you look limit, not the same, sorry, but limit x to negative infinity. As x goes to negative infinity, if you look at this graph, you can see that it keeps going down. So y is also going to be going to negative infinity. So we put y equals negative infinity. And then when x equals infinity, limit x and an arrow pointing to infinity, y equals infinity. Okay, before I give you guys some questions, any questions on any of that? I know there was a lot of content we just covered right there, and it went pretty fast. All right, if not, I'm gonna go ahead and give you guys some questions here. All right, all right, so work on these two questions, and once you've completed the two of them, just say them aloud in the chat, or say them aloud, or put them in the chat. Pause the recording. All right, so how we got the solution for that? If we just draw out the graph, right? So 7x and x squared. So the degree on top is 1, so n equals 1, and the degree on bottom is 2. So m equals 2. So since m is greater than n, our horizontal asymptote, HA, equals 0. And then after that, right away, we know that when x is going to negative infinity and x is going to infinity, it's going to approach the horizontal asymptote, which is 0. But I'll just give you guys a rough sketch of the graph so that you guys can see as well. That's going to be a vertical asymptote. That's going to be a vertical asymptote. Horizontal asymptote. And then it will be something like that, that, that. All right, that's going to be our graph. So you can write limit x to negative infinity, y equals 0, which is our horizontal asymptote, and limit x to infinity, y equals 0. So those are our two limits. And then for our horizontal asymptote here, the degrees are equal, so we just put top coefficient over bottom coefficient. So our answer is 5 over 2. And in pre-cal, many teachers are going to be pretty specific that you need to put y equals when you're asked for the horizontal asymptote. So just make sure you guys don't forget that, or else it's usually like 1 to 2 points off. All right, we'll ignore that workspace. Okay, now let's move on to the next topic, zeros. So zeros come from the numerator. So we talked about factoring earlier, and it's going to show why over here. So the zeros come from the numerator. So anything that's left on the numerator on the top is going to be one of your zeros. And anything that's left on the bottom that doesn't cancel out is going to be a vertical asymptote. And things that do cancel out are going to be wholes, but we'll look at that in a second. First, let's look at zeros. Value that kills the numerator and denominator is a whole, not a 0. Yeah, correct. Okay, here, let's factor this out. X squared minus 9. So that's going to factor out to x plus 3 and x minus 3. And you can see that through difference of squares. X over x plus 4. So right away, since our bottom x plus 4, what makes x plus 4 0? That's going to be negative 4. So right away, we can tell that our vertical asymptote is going to be at negative 4. and our zeros are going to be at -3 and 3. So therefore, you can tell the zeros in the vertical asymptotes do this. So always think about first factor it out and then look at what makes the equations zero. So here on the top, it makes it -3 and 3. So those are going to be our normal zeros. On the bottom, it's -4. So that's going to be our vertical asymptote. And you can just kind of think about it, right? Because anything, if the top is zero, then whatever you divide the bottom by, it's also going to be, uh, it's just going to be zero, right? And if the bottom's zero, then it's always going to be undefined no matter what the top is. So you can just think about it like that. Now let's look at zeros with no asymptote. Oh yeah. Yeah, here there's going to be no vertical asymptote, right? Because you can see x squared plus 1. This is like what we did earlier. X squared plus 1 equals 0. There's no way that x can equal anything here to make uh the equation 0. So therefore, there's no vertical asymptote. And as for the zeros, x squared minus 4, it's difference of squared. So we can factor that out to x plus 2 and x minus 2, which gives us our zeros at -2 and 2. So because of that, 0 at -2, 0 at 2. Then let me scroll over. Wait, let me check if there was an example list. No, that's good. Okay. Yeah. Now, quickly, you guys can look over this and find the zeros and then say them out loud or put it in the chat. All right, I'm going to solve these questions in 3, 2, 1. All right, let's go. First, let's use this a little bit. Okay, so this question is asking us to find the zeros. So let's do our first step, which is always to factor. So the top becomes x minus 4 and x plus 4, which we factored through difference of squares. And then our bottom is going to be x minus 1. There's no more factoring to that. So our bottom, the vertical asymptote is going to be 1 since that's what makes it 0. But that's not what it's asking for. So our zeros are when the top becomes 0. So top becomes 0 when x equals 4 and x equals -4. So we can put x equals 4, comma, -4. All right, now the zeros over here. Let's again factor. So the top becomes x plus 3 and x plus 2. And the bottom becomes, it stays as x plus 2. All right, now something interesting happens. There's an x plus 2 and an x plus 2 on both the top and bottom, right? And when there's something on both the top and bottom, the bottom would be a vertical asymptote, the top would be just a 0, they would cancel out. So it's going to create what's called a hole. So before I tell you what a hole is, I just want you guys to think about it conceptually, right? So normally we say whatever makes the top 0, like just that's going to be one of our zeros since whatever's on the bottom, uh, it can't make it like anything other than 0, right? Like if the top is 0 and you divide by 200, it's still going to be 0. Except there's one exception to that, and that's when the bottom is also 0. So if the bottom is 0 and the top is 0, then they're going to cancel out. And it can't equal -2 because if it's -2, then there's a vertical asymptote, right? So it's going to create what's called a hole. And I'm not going to draw the actual graph, but I'm just going to show you guys what a hole is. So hole, let's say the hole was at 2 instead of -2. And that's going to be a hole. So it's going to be a circle in your graph, and you're not going to normally you'd like draw around it. So yeah, it's like that. Then, yeah. Okay. So now next topic. vertical asymptotes. Okay, so we've already pretty much went through this throughout our things, but I'll just tell you guys quickly. So vertical asymptotes here, it's whenever it makes the bottom zero. So x equals 2 and x equals -3, it makes it 0. Now, here's one addition to what I told you guys earlier. So if you want to find the limits for vertical asymptotes, you're gonna have to use this little negative and positive side on the left and right. So basically, if you write limit, this is when you're not going to infinity, right? Let's just say limit x equals x is going to 2, since a vertical asymptote is 2. Well, it could be going to 2 from both the left side or the right side. So we have to consider both of those possibilities. So here, limit x to 2 from the left side, so is a minus. So how you can remember that is it's coming from the negative side, so it's minus. And then y equals whatever it equals. So if we look at this graph, it's going to be like vertical asymptote there, vertical asymptote there, and then our horizontal is going to be here, 0. And then that is going to be like, and then if we do -2, okay, then it's just going to be something like this. No, sorry. It's going to be like this. So because of that, and if we plug in a point over here at, let's say, -4, since our vertical asymptote here is at -3, then the top will become -3, and the bottom will become -2 times -1, which is 2, -3/2, which is negative. So, all right. You guys don't know have to know all of that for now. I'm just gonna just draw out the graph to show you guys what I mean. Okay, so as x is approaching 2 from the left side, y is going to be infinity, and when x is approaching 2 from the right side, x 2 from the right side, y equals negative. And it might seem pointless since both of the, I mean, sorry, still infinity. Yeah, it might seem pointless since both of them are going to infinity, but there are going to be graphs where they alternate. And a neat trick is when the degree, like the greatest degree on either the top and bottom is an even number, then both the arrows are going to point the same way. So here it's 2, so that's even. So both the arrows are going to point like that. And then, okay, let's look at this. Here's an example, one vertical asymptote, x at -2. And then here's our little limit thing. As x is approaching -2 from the left side, this is kind of formatted weird, y equals -infinity. And here you can see the degree, the greatest degree is 1, so therefore they're going to be going at opposite sides. And then it's like that. And here, vertical asymptote at -3, vertical asymptote at 3. Then it's going up. So a limit statement here would be lim x to 3 from the right side, y equals infinity. Okay, now let's give you guys some questions. All right. So what are the vertical asymptotes and limits when limits at the vertical asymptotes? And no, only give me the limit at the vertical asymptote x equals 5. Don't bother about -5. And is there a vertical asymptote at x equals 1? And then explain why not. Why or why not. Okay. I'll give you guys a couple of minutes to do that. All right, I'm gonna go ahead and solve these two questions in 3, 2, 1. Oh yeah. So first, vertical asymptote. So the first thing we do always is factor. So 2x over x plus 5 and x minus 5. So that means our vertical asymptotes are going to be at 2 points. So VA equals, you're going to write x equals -5, and you should write x equals 5 too, but I'm just going to write a comma and write 5 since to save time. Okay, now let's look at our limits. So how do we solve our limits? And we're just looking at the limits for when x equals 5, so we don't have to look at both of them. So 2x over x plus 5x minus 5 is going to be our graph. So draw it like that. Let's say this is when x equals -5. This is when x equals 5. Also, we know that the bottom degree is greater than the top degree, which is 1. So therefore, the horizontal asymptote is going to be at 0. Now, how we solve this is we're gonna plug in points to see, and since this is x equals 5, we only have to plug in points near x equals 5. So let's plug in 2 points. First, let's do 6. So to do that, 2 times 6, because we're plugging in 6 for x, and then over 6 squared minus 25. 6 squared is 36. 36 minus 25 is going to be 11. So 11, 12 over 11, since 2 times 6 is that. So 12 over 11, that's our point for x equals 6. So that's going to be like somewhere, we'll say like there. Okay, good. So now we know that this graph is positive, and it's going to be following our asymptote. So we can't have any points like here, because that's not where, and then this guide point, we can use it. Now we just follow our asymptotes. So now we can see that limit x approaches 5, and that's from the right side, the positive side, positive infinity. So we write plus x approaches to 5 from the right side, y equals infinity. Now let's play a point to the left of 5, 4. So we're going to do the same process. 2 times 4 over 4 squared minus 25. And what we're doing here, again, we're just plugging in points for x. So we're plugging 4 for x. And why we did 6 first is because 6 is a little after x equals 5. So then we know that like what's on this side, the very right side. And now to find the middle like area near x equals 5, we're doing 4, which is 1 less than 5. So we get 8 over 9. So it's going to be 4 comma 8 over 9, which is like there. But to double check, let's plug in like one more point. Let's This time let's plug in a point on this side, because we know this side is going to be the opposite, right? So let's plug in a point at x equals -4. So that's going to be -8 over. Oh wait, by the way, this is going to be -9. So -8 over -9. So this is going to be 8 over 9. So sorry, this isn't going to be 8 over 9. This point is going to be -8 over 9. And this point, it's going to be just 8 over 9. So this graph would go something like this probably. So then you can write limit x approaches 5, and this time from the left side, so negative side, y equals -infinity. All right, nice. Now, is there a vertical asymptote at x equals 1? So the answer to this is going to be no. And let's look at why. So first, the x minus 1 and x minus 1 cancel out. So now it's just 1 over x plus 6, which you might be looking, okay, there's no vertical asymptote, there's nothing, it's just -6, right? But this is the original equation is still going to be x minus 1 over x minus 1 times x plus 6. So although there's no vertical asymptote there, there's going to be just a hole at that point. So this graph would look something like let's say this is like x equals 1, right? So let's plug in a point near 1, which is 2. So 1 over, then it's going to be like 2 comma 8. So I'm just going to plug in points to show you guys this. You guys don't have to do this part. -1. Okay, so let's say there's like a hole here, right? And then there's going to be a vertical asymptote here. So it's just going to skip over that point. So there's no point there. It's a hole. So therefore, there's no vertical asymptote, and that's why. All right, holes. Again, now we're actually looking at holes. A hole is a factor that cancels top and bottom. So the x value from the canceled factor, and we plug it x into the reduced function, and that way we get our point for the hole. So let's do let's do factoring for this. X for our model function, x plus 3, x minus 3 over x minus 3. So now so now we have our hole is going to be x minus 3. So that's going to be our x point for the hole. And now to find our exact y point for the hole, here's how we do it. So x equals 3 is going to be our hole, right? And then for the y point, we just plug that back in. So since x minus 3 cancel, our function is just x plus 3. And to find the hole, we just plug x in. So 3 plus 3 equals 6. And since our hole I just cut out there. Going back now. Okay, so x equals 3, so we're plugging in that point. So since our hole is at 3, we know that the x value of the hole is 3. And now we just plugged in 3 for 3 plus 3 because our graph left over is just x plus 3. And therefore, our y value for our hole is going to be 6. Anybody have questions on why that is? And like, you guys understand how I got the value for the hole? What I did was basically after I canceled out the two functions for the hole, what I had left over was just x plus 3. So you plug in the x value for the hole in the leftover equation. So here, let's look at x squared minus 4. Factor out to x minus 2, x plus 2 divided by x minus 2. So we can see that our x minus 2 canceled out. So our hole is going to be at x equals 2. And since the function left over is x plus 2, now we just plug in 2 to this. So 2 is x now. So 2 plus 2 equals 4. And since our hole is at 2, our hole is going to be at 2 comma 4, which is shown right here. Now let's look at where there's a hole in asymptote. So here cancels out. X minus 2 is canceled out. So now our function left over is x plus 1. Our hole is going to be at x equals 2 since that's what makes these 2 points 0. So now x equals 2, and we plug that in here. So then 1 over 3 because 2 plus 1 is 3, and then on the top is just 1. So our hole is going to be at 2 comma 1 over 3. So now we know where our hole is. And we still have a vertical asymptote right here at x equals -1 because x equals -1 when it's 1 over x plus 1. So that equals -1 to make the bottom 0. And now I'll give you guys some example question. Or sorry, that's the same examples. Here's the questions. Okay. Find the hole for the first question. And for your second question, find any holes and vertical asymptotes. So always remember that the first step you're going to do on these type of questions is going to be to factor, and then cancel out to find the holes, and then whatever's left over is going to be your vertical asymptotes. And give me the exact points for your holes. All right, I'm going to solve this in 3, 2, 1. Okay, so the first question, find the hole. So first thing we do, factor. So x minus 5, x plus 5. And then you can see that the denominator is just going to be x minus 5 since that just stays the same. Then these two cancels out. So what we're left with is x plus 5. And the whole is going to be at x equals 5 since that's where these two cancels out. X minus 5 is what cancels out. So that's going to be equal to 0 when x equals 5. So that's going to be the x value of our whole. And so find the y value. We plug in the x value to the equation where the rest of it isn't canceled out. So this part is what we're left over with. So we plug in 5 to that. So 5 plus 5, that equals 10. So our whole is going to be at 5 comma 10. Any questions on that? All right. And then here we find the wholes in vertical asymptotes. So to get, first we factor the top, x plus 2, x plus 1. There we go, factor the top. And the bottom is x plus 3, x plus 1. So x plus 1 cancels out. So we know that this is going to be a whole at x equals -1. And our y value, since x plus 2 over x minus plus 3 is what's left over, let's plug in x equals -1 at these points to find the y value of our whole. So -1 plus 2 over -1 plus 3 is going to be 1/2. So our whole equals -1 comma 1 over 2. Okay, good. Now let's look at the rest of our equation, x plus 2 over x plus 3. So x plus 2 is going to be our x-intercept since that's what makes it 0 at the top, but we don't even need that. Our bottom, x plus 3. So x plus 3 equals 0. And then to solve for this, we just subtract 3 on both sides. So x equals -3. So our vertical asymptote is at x equals -3. And that is going to be our solution to this problem. Now, we'll go over everything we learned in this video today with this question right here. So I want you guys to give me 4 things: the zeros, vertical asymptotes, holes, and end behavior. So, and for the end behavior on this, I want you guys to write, normally we've been doing limit x to, let's just say infinity, blah, blah, blah. You guys are giving me y. Since this function is actually f of x equals the function, you have to do f of x equals, and then you just write whatever and behavior it is. All right. So you guys can solve this right now, and I'll solve it in a couple minutes. I'm gonna go ahead and solve this question now in 3, 2, 1. Oh yeah. So the first thing we need to do, factor. So let's factor at the top, x plus 2, x minus 2. And then let's factor the bottom. It's gonna be x plus 2 and x minus 3. So first thing we notice, these two cancel out. So we do have a whole at x equals -2. So first thing let's do is find where that whole is. So let's plug in, what we have left is x minus 2 over x minus 3. So x equals -2. So -2 minus 2 is -4. And -2 minus 3 is -5. And this -4 over -5 is just 4 over 5, which is 0.8. But we'll just write our whole is going to be, does that look like a 6? 5. We'll write our whole is going to be at -2, comma, yeah, we'll write 0.8. And since we've dealt with our whole, now we can just ignore that portion of the equation. So all we have left now is x minus 2 over x minus 3. And we have to look at what makes the top bottom. That's going to give us our 0. So x minus 2 equals 0 when x equals 2. So our 0 is going to be at x equals 2. Then our vertical asymptote is what makes the bottom 0, which is x minus 3. Let's get rid of this since it's taking so much space. So our vertical asymptote is going to be x equals, where's this portion? 3. And then let's look at horizontal asymptote. Let's look at our original equation, x squared minus 4 over x squared minus x. So our base degrees are x squared on both, and the degrees equal on both. So we have to get the leading coefficient over the leading coefficient. The coefficient on the top is 1, bottom is 1. 1 over 1 equals 1. So our horizontal asymptote is going to be at y equals 1. And since we have our horizontal asymptote, we can easily find our end behavior without even looking at the graph. It's going to be limit x to infinity f of x equals 1. And I'm gonna write it here so I have more space. Lim x to negative infinity f of x also equals 1. That's gonna be our final answer. So any questions on that right there? All right, if not, thank you guys for joining and paying attention the whole time. I do appreciate it. And the recording of this video and all the questions included are going to be posted on YouTube at Beyond the Formula Tutoring. So you guys can see them over there. And with that being said, I'll see you guys next time.